In this pre-calculus algebra video, we will look at some applications of exponents and logarithms. These are exponential growth and decay problems. One of the problems we'll look at is a logistic growth function as well. To start with, here's an example that can be modeled with an exponential function, tooth decay. One of algebra's many applications is to predict the behavior of variables, and this can be done with exponential growth and decay models. With exponential growth or decay, quantities grow or decay at a rate directly proportional to their size. Populations that are growing exponentially grow extremely rapidly as they get larger because there are more adults to have offspring. In this section, we're going to explore how to create such functions and how to use them to make predictions. A quick review of the graph of exponential functions. We could have a model that is growing, so we're increasing. When you read the graph from left to right, we can see that this is increasing. Or we could have an example of a decay model, where when we read from left to right, we see that it's falling or decreasing. Here's our first example. In 2020, the population of Israel was approximately 8.7 million. By 2050, it's projected to grow to 12.7 million. Just to start with, I'm going to make a chart here, putting this information. In 2020, we're told that the population was 8.7 million, and we're expecting that in 2050, it'll be 12.7 million. So a couple things we can look at here is that the difference in time is 30 years. 30 years have lapsed. And then we can use this model, the exponential growth model, A equals A naught e to the kt. When we see this A sub 0, we read that A naught. So it means the initial amount. So the amount, in this case, the population, in the future population, is equal to the initial population, so that's going to be the starting point, the 8.7, times e to the kt, where t is the number of years that have passed, and k is the special constant that demonstrates the relationship of the population from one year to the next in this particular problem. So k is a growth constant, and what we need to do to start with is to actually find that growth constant, or in some cases, other cases, it'll be a decay constant. But the first step in understanding or being able to apply an exponential growth model is to be able to find that constant for the information that's described, which is k. Here's how we could go about doing that using logarithms. We're going to start with our equation, and I'm going to recommend that every time you do this, that you actually write the equation, and then we're going to write what we know. We know that the future amount is 12.7. We know that the initial amount is 8.7, and we know that the number of years that passes, this is from 2020 to 2050, is 30 years. Now I can simply plug those values in. Let me move this off. We can plug those values in to the equation. So in place of A, I'm going to put the 12.7. In place of A naught, I'll put the 8.7, and then we multiply this by e to the, in place of t, I'll put 30, and then k. Here's what that's going to look like when I fill those values in. A is 12.7, A naught is 8.7, And then k is what we're trying to find, and we know that the time is 30. I can now solve this equation with a log. Specifically, I'll use a natural log because we have an e in the problem. And you could ask yourself this question. I don't know if you're getting tired of hearing this, but here's the tree, and we've got an x, in this case a k. Let me change it to a k. We've got a k stuck up in the tree. How do you get the k down? We throw a log at it, right? When the log hits the k falls down. So specifically in this case, since we have an e, the base of a log that we want to use is log base e, or in other words, the natural log. So what I'm going to do is take the natural log of both sides. I'm going to take the natural log of both sides. So I have the natural log of 12.7 is going to be equal to the natural log of 8.7 e to the 30k. Once I do that, this exponent will fall. That's how we get the exponent down from the tree, but it's going to carry with it the 30, right? So when we have a log, it's equivalent to when we have a log of something with an exponent, it's equivalent to the product of that exponent times the log. So in other words, this 30k can fall down to the front. Now to solve for k, now that I've written the formula and written what each value is equivalent to, I can fill in those values. So in place of a, I'll put the 12.7. In place of a naught, the initial amount, I'll put 8.7. And in place of t, the number of years that have gone by, I'll put 30. Now I'll be all set to solve this equation for k. Remember, what I'm trying to do is find k. K is the only variable here because e is a constant. Just like pi is approximately 3.14, e is approximately 2.7. It's a constant like e is. So we're not looking to find e, we're looking to find k. The first thing I'll do to solve for k is divide both sides by 8.7. So I have 12.7 over 8.7 equals e to the 30k. And then how do I get a k down from the tree? How do I get this k? Let's see, exponent down. You guessed it, we're going to throw a log at it, right? This log will knock the k down with the 30 also. And here's what it would look like if I take the log. In this case, I'm going to use the natural log. If I take the natural, so that's just log base e. When I take the natural log of both sides, this 30k will fall down to the bottom, so it comes down in front. And then the natural log of e is just 1. So I have the natural log of 12.7 divided by 8.7 is equivalent to 30k. Let me write that out to make sure everyone is with us. You don't necessarily need to rewrite this each time, but let me write it to make sure we haven't lost anyone yet. And then what would you divide both sides by if you wanted to solve for k? If you said divide by 30, you're correct. And that's it. So I'll type this into my calculator. It can be a little tricky when you're first learning how to type these into your calculator, so follow along with each step carefully. Here's what I'm putting on my calculator. I'm going to find the natural log button. Notice that's an ln, not a 1n for log natural. So I hit the log natural button, the parenthesis opens up already, and then I'll put 12.7 divided by 8.7, and then I'll close the parenthesis, and then divided by 30, and that gives me that k is approximately 0.012609. My calculator is giving me 9299. If I wanted to round this to 4 decimal places, I'm going to round to 0.0126. So I could now say that k is 0.126. So what does the growth model look like? It would look like this. We could go back to our a equals a naught e to the kt. And what I'm going to do is I'm going to replace the k in that equation with the value that we found for k. So it would look like this. A equals the end amount equals the initial amount, 8.7, e to the 0.0126 t. It is an approximation, so if you were working this problem out in the future, you'd want to keep this natural log of 12.7 divided by 8.7 all over 30 in your calculator and use the precise calculation, because you don't want to typically round in the middle of the problem. Okay, we can continue to answer further questions about this model. Here's an example. In which year will Israel's population be 10 million? So in other words, find t when the amount A is 10. I've got the growth model from the other page. The amount is equal to the initial amount of 8.7 times e to the kt, so 0.0126 t. And then I can replace the a, the amount, with 10, because that's the amount we're given for this question. And when I replace the a with 10, I can divide both sides by 8.7. So I have 10 divided by 8.7 is equal to e to the 0.0126 t. Now that I have it simplified to this form, I want to get that t down from the exponent, so get it down from the tree, right? So how do I get that down from a tree? I can take the natural log. When I take the natural log of this expression, e to this exponent, then the exponent will come down. So if I'm taking the natural log of the right side, I'll need to take the natural log of the left side also. So it's going to then look like this. We'll have the natural log of 10 divided by 8 7/10 is equal to 0.0126 t times the natural log of e. Well, that natural log of e is 1, because if you recall what that means, it means log base e. Log base e of e is saying, okay, so if I took the e, what exponent would I need to get an e? Well, that answer is 1. So the natural log of e is just 1. So I'm almost there with solving for t. All I'll do now is divide both sides by my constant, 0.0126. And that's it. My exact t is a natural, well, it's still not exact because we do have an approximation for k, but we'll live with that. And I am going to ask that when you do the examples that you round your k to 4 decimal places like you see here, and that'll be fine. The natural log of 10 divided by 8.7 divided by K, which is 0.0126. And approximately, when I put this into a calculator, I'm going to type in ln, natural log, or log natural, 10 divided by 8.7, and then close the parenthesis, divided by 0.126, and that gives me approximately 1.1052. There's 4 decimal places, so that is, let me check that one more time. Yeah, I think when I initially wrote that, I put the decimal incorrectly. If you put that on your calculator, did you get 11.052? So ln 10 divided by 8.7, close parenthesis, divided by 0.0126. And that's going to give us approximately 11.05. Rounded to the nearest number of years would be 11 years. So 11 years after, let me jot this down, 11 years after our initial year of 2020 is going to be 2020 plus 11, or 2031. So to answer this question, in which year will Israel's population be 10 million? If it continues on this growth pattern, it's going to be 2031. Let's try another example. Here's a logistic growth function example. It's a little bit different, but if you can follow a couple pieces of this, it's not really challenging. You just have to be able to read and pull out of the problem the information that it's giving. So we are given a growth function, f of t is equal to 100,000 divided by 1 plus 5,000 times e to the negative t. And this describes the number of people, f of t, who have become ill with influenza t weeks after its initial outbreak in a particular community. How many people were ill by the end of the 4th week? So at the end of the 4th week, we're saying that t is equal to 4. So all that this is asking us to do is find, if I want to interpret this problem, it's just saying find f of 4. Find f of 4. Well, f of 4 is going to equal 100,000 divided by 1 plus 5,000 e to the negative 4. Why am I making the 4 negative? Look at the function that we're given again, and it's e to the negative t, right? So e to the negative 4. And if I put this in my calculator, I can get a really good approximation. Here's what I'm putting in the calculator. And you've got to be careful with the parentheses here, because notice that we're going to divide not just by 1, but you've got to put this in a calculator so that your calculator knows to divide by this entire quantity. If we type this in without the parentheses, we're going to have 1,000 divided by 1 and then add this 5,000. What we want to do is divide 1,000 by this entire sum, 1 plus the 5,000 e to the negative 4. Here's what it would look like on the calculator. 1,000, 100,000, divided by, and I'm going to insert a parenthesis. You'll have to be careful because at the end we're going to have a double parenthesis. So 1,000 parenthesis, 1 plus 5,000, and then I'm going to put in e to the x. To get to that on my calculator, I have to go to second ln, and it types in the e caret, and then it opens a parenthesis. That's where I'll type negative 4, close the parenthesis, but that's closing the parenthesis for the negative 4, and I've got to close the parenthesis one more time. If you've done that like I have, you would get 1080.1679 So how many people would be ill? Therefore, 1,080 people would be ill by the end of the 4th week. And the biggest challenge here really is just typing this into the calculator. So practice with your calculator and make sure you're comfortable with how that works for your calculator. Now, what is the limiting size of the population? The limiting size is always just the numerator. So in this case, we're not doing any calculation. We're just pulling that out. Limiting size of the population in this case is 100,000. 100,000. So what they're saying is they're not expecting more than 1,000 people, or 100,000, I'm sorry. They're not expecting from this model more than 100,000 people to get sick during this illness. So the limiting size of the population is 100,000. Let's look at another example, a scatter plot. Given some information in a table, the table shows the percentage of miscarriages by women of various ages. We could create a scatter plot. To create a scatter plot, I've created a y and x axis. The x axis is going to be the women's age. That's usually the first column. You could do it opposite, but typically it's going to make the most sense if we put the x's, the first variable on the x-axis, and then the percentage of miscarriages on the y-axis. By glancing through this, I saw that the highest percent was 52 and the highest age was 47, so I stopped at 60% in 50 years. And then I just plotted each point, 22.9, 27.10, 32.13, 37.20, 42.38, and then 47.52. And the question is, determine the type of function that would be a good choice for modeling this data. So it looks to me like this data is following, if we were to draw in a line of best fit, if we were to draw an approximation of what we think it looks like, so we can speculate on how it's going to continue to grow, that looks like an exponential function, doesn't it? Exponential. So it's an exponential function that models that data models. Number 4, we could rewrite a function in terms of base e. This is a little bit different, but follow along, and then I think that the example will make a little more sense. Here's what we're given. Y is equal to 100 times 4.6 to the x power. And if we want to write this in terms of base e, here's what we can do. We could write this as 100, or y equals 100 e to the, we could raise this to the power, e to the natural log of 4.6 times x. So we can rewrite this taking the natural log of 4.6. So we have the natural log of 4.6 to the x power. When I then use my calculator to find the natural log of 4.6, I'd get y equals 100 e to the 1, I'm going to round it to 3 decimal places. The natural log of 4.6 is approximately 1.52. Natural log of 4.6 is approximately 1.526. Are you getting that on your calculator also? So y equals 100 e to the 1.526 x. And that's all that they're asking us to do here, to rewrite this in terms of e. That's all that we'd have to do. And that wraps up the examples in this section for the notes. If you have questions about these examples, I hope you'll ask. If you struggle to really comprehend these examples, I'm going to encourage you to use your textbook to walk through more of the examples that are completed in the textbook, and then bring your questions with you to class so that we can go over even a few more details.